So we started in chapter 6. So we did quite a few things in chapter 6, but the one thing that I want you to know how to do is doing integrating factors, which may have been the hardest part for you guys. So I'm going to work through an example and talk about the whole process. So this is a first order linear differential equation. So the first step is to put it in standard form. So what we would do is we'd move the term involving y to the left-hand side so that all the terms involving y or y prime are on the right-hand side. And then we have to get into a form of y prime plus p of x times y is equal to q of x. So you can see I have y prime times x squared, so I'm going to have to divide everything by x squared. So I'll get y prime plus 3x divided by x squared y is equal to x cubed divided by x squared. I mean, here I have x squared divided by x squared, so that ends up being y prime plus 3 over x times y is equal to x. So that's standard form. So first step, put it in standard form. Then you need to find what the integrating factor is. So the integrating factor is equal to e to the integral of p of x dx. So p of x is this term that's in front of the y after you put it in standard form. So in our case, p of x is equal to 3 over x. So the integrating factor u of x is e to the integral of 3 over x dx. And if we factor out the 3 out of the integral sign, you'll have 3 times the integral of 1 over x dx, which is, the integral of that is the natural log. So we have e to the 3 times the natural log of x. And before you can use the inverse properties of logarithms and exponential functions, you need to bring the 3, or whatever the coefficient is in front of the natural log, inside. So we'd get natural log of x cubed. So now you can use the inverse properties of logarithms and exponents. So we get x cubed. So this was like the one we did on the test. I gave you one where the integral ended up being the integral of 1 over x dx. Now, am I going to do that on the exam? I don't know yet, but I'll show you the other option, what would happen if it wasn't something like the natural log. But in this case, we end up with this nice situation where we have e to the natural log of something, and so the integrating factor becomes that something. So then what we can do is we can use that integrating factor to multiply the original differential equation in standard form by to make something magical happen. Yes.
We have a conflict with an autism group that has reserved this for
Oh, have they? Okay. What time is that?
Can we move you all to...
Okay, so we're going to multiply every term in the original differential equation in standard form by x cubed. So that'll give us, well, yeah, that's right. Okay, so what we get is we get x cubed y prime plus 3x cubed over x, oh, I forgot a y here, over x times y is equal to x times x cubed. So that means we have x cubed times y prime plus 3x squared y is equal to x to the 4th. And the key thing here is that if I look at the derivative of x cubed, I get 3x squared. That's the whole idea behind integrating factor is so that the second term here that's a function of x is the derivative of the first term that's a function of x. And this y prime is the derivative of y. So you can use the product rule backwards to rewrite. So we can compress this left-hand side and make it x cubed y prime, x cubed y quantity prime, and that equals x to the fourth. So if you multiply both sides by dx and integrate, when you have, I forgot the dx part here. So when you multiply this by dx, this is the derivative of x cubed y with respect to x times dx. So when you integrate this, you just get the expression that's in the parentheses. And then on the right-hand side, you just use normal integration rules. So you get x to the fifth over 5 plus your arbitrary constant c. And then finally, you divide by whatever this integrating factor is in front of y. You divide every term by that. So this x to the fifth will become x squared, and c will become c divided by x cubed. So you always end up with this c over something or other. It's not just c by itself, but it's c divided by or multiplied by something. And then our initial condition that we had, which I've got to dig out of my bag. So I just kind of threw everything in here. So I had the initial condition that y of 2 equals 5. So you put 5 in for y, and you put 2 in for x. And you just do a little fraction and stuff. So you get 4/5. 5 is equal to 4/5 plus c divided by 8. You'd subtract 4/5 on both sides. So 5 is 25/5. So you have 25/5 minus 4/5 is equal to c over 8. And 25 minus 4 is 21. 21/5 is equal to c over 8. And you can solve for c. C is going to be equal to 168 over 5. 21 times 8 is 168. And then finally, I want you to write out the final equation. So once you've found c, then you can say y is equal to x squared over 5 plus 168 fifths divided by x cubed. Or I guess it would look better if we just put that in the denominator. 168 over 5 x cubed would work out. Okay, so that's one scenario. And that, again, that happens when p of x is some constant multiplied by 1 over x. And so when you integrate it, you end up with e to the some number times the natural log of x, and you take that exponent inside inside the natural log, and then you use the inverse properties of logarithms and exponents. The other option would be if it's something that's not 1 over x. So let's just think about what we would do in that situation. So if you got your, let's say your first order linear differential equation ended up being something like 3x times y is equal to, I got to make sure something. Okay, I'll decide the something in a second because I want to make it so it'll work out. So what you would do in this case is p of x would be 3x instead of 3 over x. And when you calculate the integrating factor, you'd have e to the integral of 3x dx. And the integral of 3x dx is going to be 3x squared over 2. So the integral of x is x squared over 2. So the integrating factor that you're going to multiply by would be 3 times 3x squared over 2. So I'd have to choose some kind of quantity over here that would make things work out, which would be anything that involves the derivative of x squared, which would be x, I guess, right? So I'm going to put x in there. So that's my original differential equation. Would be y plus 3x. Y is equal 3 y prime. Forgot the y prime part here. So y prime plus 3x y is equal to something. Again, I would choose, if I were to give you this problem, I would choose something where this can be integrated reasonably easily. So when you take these first two terms multiplied by the integrating factor, you'd end up ultimately with e to the 3x squared over 2 times y prime, y, the whole thing times prime. So you take the derivative. So this times that plus this times that could be collapsed into the integrating factor times y, just like we did in the previous problem. And then over here, you'd end up with x times e to the 3x squared over 2. So when you integrate both sides, multiplying by the dx, on the right-hand side, you'd end up with the integral of x e to the 3x squared over 2 dx. And so you could use u substitution. U would be equal to 3x squared over 2, or du would be 3x dx. So you see I've got x dx, so I want to I'd solve for that. X dx equals du over 3. So when you integrate the left-hand side, it would end up being the integral of e to the u times du over 3. And the integral of e to the u is e to the u. So you'd end up with 1/3 e to the u plus c. And u would be equal to 3x squared over 2 plus c. So then you'd end up with that. On the left-hand side, the integral of e to the 3x squared over 2 times y would just be y prime, this whole thing prime dx would just be that expression in the integral in the parentheses. And then you can see I could solve for y. If I divided every term by e to the 3x squared over 2, I'd end up with 1/3 plus c divided by e to the 3x squared over 2, or y is equal to 1/3 plus c e to the minus 3x squared over 2. So I've just moved that from the denominator to the numerator. I mean, either one's fine. So that would be the other kind, is where you end up with e to some exponent. And I would choose the right-hand side to turn out to be something that would be reasonably easy to integrate. You know, if I chose x squared, you'd have to use, I don't know what you'd have to use. Maybe integration by parts, but it wouldn't be that easy. Well, yeah, it'd be a hard integration by parts. You'd have to say u is x and dv is equal to x e to the 3x squared over 2, but you know, that's, I would, if I were to do the second scenario, I would make it so that the integral on the right-hand side, after you've applied the integrating factor, would be something that would be solvable by a reasonably simple u substitution. Okay, so that's that's chapter 6. That's all I'm going to test you on in chapter 6 is an integrating factor problem. Okay, turning over the page. Um, this says find the volume of the solid generated by rotating the area bounded by the functions y equals x squared, y equals 1/4 x, and x equals 4 around the x-axis using the washer method and the y-axis using the shell method. So you want to write all those formulas down. By the way, you get, just like last time, you get whatever, how many tests do we have? 4 plus chapter 10. So you get 5 sheets, 5 cheat sheets if you want to use that many. So you can put the formulas down. Also, you can bring in that. So what else can you bring in? You can bring in your integral table and your trig identity table. So that's on the same sheet of paper, so you don't have to memorize any integrals. So I guess that's all. You won't need there will be nothing out of chapter 9 on the final, so you won't need that handout. Okay, so the area looks like this. You've got y equals the square root of x. You've got y equals 1/4 x, and you've got x equals 4. And we're doing the washer method around the x-axis and the shell method around the y-axis. What this does is it gives us a case where we have the same rectangle. We'd have a vertical rectangle. And as a consequence, we're going to integrate with respect to x, because we'd stack these rectangles up in the x direction. So you'd have on your sheet the washer method x-axis or horizontal axis, and the formula is the volume is equal to pi times the integral from a to b of capital R of x squared minus small r of x squared, whole thing times dx. So you look at what curves bound this rectangle on the skinny parts, and the skinny parts are this side and this side. So in this case, capital R of x is the square root of x. And small r of x is equal to 1/4 x. And a is equal to 0, and b is equal to 4. So the volume would be equal to pi times the integral from 0 to 4 of the square root of x squared minus 1/4 x squared times dx. And I'm not going to work through the entire integral here because it's just I'm going to simplify it. So if you square the square root of x, you get x, and if you square 1/4 x squared, you'll get 1/16 x squared. So you square the fourth and you square the 4, and you multiply by dx, and you solve it. Okay, so I'm sure you guys can do that. Evaluate it between 0 and 4. It's just a simple polynomial integration. And most likely that's what I'll have on the test. It'll be a I wouldn't say simple, but it'll be a polynomial integration, which you guys are good at. And then if you have the shell method around the y-axis, the formula there is 2 pi times the integral from a to b of r of x times h of x dx. And we said that, or actually it's p of x, isn't it? We use p of x. So p of x, when you rotate around the y-axis, is just x. And h of x is the same two functions that defined the outside and inside radius for the washer method, but you don't square because you're looking for the difference, not the difference in the squares. So then you can just plug, and a and b are the same. So the volume is going to be 2 pi times the integral from 0 to 4 of x, which is p of x, times h of x, which is the square root of x minus 1/4 x dx. This one's a little more difficult because you end up with a fractional exponent, but it's not that hard. If you change x square root of x into x to the 1/2, you'll end up with x to the 3/2 minus 1/4 x squared, both times dx. So again, it's a polynomial. I mean, I don't want to make this super difficult for you. I just want you to be able to show me that you can generate the equations and recognize whether you're integrating with respect to x or y. Don't assume that I'm just going to do it in terms of x. If I did it, I could do something like y equals x squared and some line that goes more vertically and come up with the same kind of problem, but it would be easier to integrate with respect to y than it would be with respect to x. So, but I'm not going to ask you to do it around an axis other than the x and y axis. Okay, so that's off the table. It'll just be one integral, so I'm not going to break it up. It's not going to be a triangle problem. So it'll be a reasonably straightforward problem involving probably either square root function or linear functions or squared functions. If I went to anything beyond a squared function, the integrals would start to become more difficult. But like I said, don't assume that it's just in the x direction. But if I do give you one and I ask you to do both methods, they'll be in the same direction. So like this one, I used the washer method around the x-axis and the shell method around the y-axis, which had the same integrated with respect to the same variable, and they had the same limits. So it was pretty easy to go from one to the other. So I'll give you one direction or the other, either the y direction or the x direction. I won't ask you to do both of them. Okay. Anybody any questions so far? Okay, and then so that's chapter 7's problem. Moving on to chapter 8. So we got a couple of problems from chapter 8 that we'll have. So there will be an integrating factor problem. And I've kind of given you an idea of what is going to be on there. It's probably going to be one of these types of problems. So let's just look at them and how you would set them up. And I may or may not ask you to integrate by parts twice. So all of these three examples here are using integration by parts twice, but I may just do once. Depends how long the test turns out to be. So you got to recognize when it's integration by parts twice and when it's integration by parts once. So actually these two, you'd have to use integration by parts twice, just like the problem on the last test. So it's probably worth looking through that. I think I posted a solution to that chapter test, so you can go back and look at it if you had issues. A lot of you got the first integration by parts correctly, but messed up the second, forgot to do it again. And also, you got to make sure you treat these exponents properly. You just end up with extra factors of, in this case, 2 or 3, depending upon the coefficient in front of the argument of the trig function, or e to the x. So I think we did those in class. Just go back and look at it. If you messed up on the test, make sure you understand why you messed up. Now the first problem is one that's different. You may look at that and say, oh, that's integration by parts twice. I'm going to let dv equal the natural log of x. But remember that, hold on just a second. The natural log is the one case where you let, so let's just work through this problem. Where you let u equal the natural log of x, and dv would equal x squared dx. All the other cases, in this case you let dv equal the sine of 3x dx, and dv equal e to the 2x. So if you take the derivative of the natural log of x, you get 1 over x, and you multiply by dx. The integral of x squared dx is x cubed over 3. So integration by parts says that the integral of u dv is uv minus the integral of v du. So we plug in u, natural log of x, times v, x cubed over 3, and we subtract the integral of u, or v, which is x cubed over 3, times du, which is 1 over x dx. So the first term becomes 1/3 the natural log of x. Actually, let's put x cubed first. That way there's no confusion about where it is. So we get 1/3 x cubed natural log of x. And the second part, you end up with 1/3, factor out the 3, x cubed divided by x is x squared, so you get x squared dx. So then you'd end up with 1/3 x cubed natural log of x, and the integral of x cubed, x squared is x cubed over 3. You'd add your arbitrary constant at that point. And so the final answer is 1/3 x cubed natural log of x minus x cubed over 9 plus c. Okay. So don't, if I give you the first kind of problem, I haven't decided yet. I haven't made up the test, so don't. These are kind of things that are rolling around in my head as far as I've done all of these in the final. It's either that one, these two, or just a single integration by parts. I always put that on the final. So just make sure you understand that. Okay. And I'm skipping over trig substitution and trig integration because I'm doing that tomorrow. Okay. It's not because we're not doing it. It's just when I was putting together my review on Friday, as well as grading the tests, I decided I needed to think about the trig substitution problem, because sometimes if I just arbitrarily pick one, I could end up with an integral that's really hard to do, and I didn't want to do that, and I was getting tired, so I decided that the easiest thing to do as far as demonstrating today would be the next example. So there will be some partial fraction problem on there. And most likely it will be a fairly straightforward example like this one. So it just involves two linear factors. So what I'm going to do is I'm going to work out the partial fraction stuff separately, and then I'll substitute it in there. So you factor the denominator. Of course, you got to be really careful about factoring, because if you don't get the factors right, you can't get the right answer. So I will, at the exam, if you're somebody who's not really confident about their factoring, you can come up and ask me, is this right? I'll say yes or no. I'm not going to tell you what the answer is, but I'll tell you if it's right or not, okay? Most of you are good at factoring, and you may not feel like you need to do that, but just so that if that's their Achilles heel is factoring, but they know how to do everything else, I don't want them to suffer too much. I'm sure they could figure it out ultimately. Okay, so we factored it. Hopefully that's right. Yep. One thing I always have to do when I make up these problems, make sure the limits don't include one of the asymptotes, which I've just done. Okay, so I'm going to change my problem here. Let's make it, yeah. So let's change this to plus 3. Okay, I've done this before where the um, the limits include one of the asymptotes, which I can't do. So I'll end up with x plus 2 and x plus 1. And that way, the vertical asymptotes are -1 and -2, which is not in the interval. Okay. So what we do, of course, is when we have two distinct linear factors, we just can cross multiply the terms in the numerators and the denominators for the two terms that we have. And what we're doing basically is we are finding a common denominator for these two terms, which is the same as the denominator here. So I'm going to multiply this by x plus 1 and x plus 1, which gives me that. And I multiply this by x plus 2 and x plus 2, which gives me that. And then I have a common denominator. Now, I want you to use this method. Don't come up with two equations and two unknowns. I want you to use the case where you choose the values of x, which cause this term to go to 0 and this term to go to 0, so that you can just solve a simple single linear equation. So I've chosen x equal to be -1. So I get 7 times -1 minus 2 is equal to a times -1 plus 1. That's going to go to 0. Plus b times -1 plus 2. So that becomes -9. And here I get just b. 2 minus 1 is 1. So I get b is -9. And then the second choice is x equals -2. So I plug that in there. 7 times -2 minus 2 is equal to a times -2 plus 1 plus b times -2 plus 2. So this one goes to 0. Here, this one went to 0. So this allows you to solve directly for a. So we got -14 minus 2 is -16. And we end up with -a. So a is equal to 9, or 16. So we got a is 16, b is equal to -9. If I did that right, let's just check here. Yeah, okay, so that's right. So now what we're going to do now is use that to rewrite the original integral. So we'll end up with 16 divided by x plus 2 dx. And I've got this negative sign from b. b is -9. So integrate from 1 to 3 of negative. I brought the negative out front. And then x plus 1 dx. So when you integrate this, you'll get 16 times the natural log of the absolute value of x plus 2 evaluated between 1 and 3. And then you get -9 times the natural log of the absolute value of x plus 1 evaluated between 1 and 3. There's no arbitrary constant c, so don't put it there. And then you can plug in your numbers. So you'll have 16 natural log of the absolute value 3 plus 2 minus 16 times the natural log of the absolute value of 1 plus 2. So that's this one evaluated. And then you'll have -9 times the natural log of the absolute value of 3 plus 1 plus, so I got a negative from the lower limit and a negative from there, so it becomes positive 9 times the natural log of the absolute value of 1 plus 1. And you get some answer. I'm not gonna work it out. You can plug that in, figure out what it is. So that's the partial fraction. You know, we had the other one where we have a distinct linear factor and a distinct quadratic factor. If I decide between today and tomorrow that I'm going to put one on the test, we'll go work through an example tomorrow. So as far as Chapter 10 material is concerned, if I don't get it covered tomorrow in class during the review, I'll just do a short little video telling you what out of Chapter 10 is involved in the exam. So you can watch that Tuesday night or Tuesday day, I guess, because I'll probably have it ready to go today once I make the test up. So tomorrow what we'll do is we'll cover trig integration, trig substitution, what else? Something else. I'm not sure yet. So come tomorrow because we'll cover the rest of the review. If we have some time left over, we'll go over the 2 problems that you guys had difficulty on the last test. So I think we'll just stop there. So we'll see you in physics. We'll stay in here, of course, instead of going over to back to the other one. And we ran 5 minutes over, so you have an additional 5 minutes. So 20 after 9.